Hello and welcome to this short introductory talk on the Gatekeeper algorithm, a new submission to ICRA 2023. The main motivating purpose for this paper is the increasing need to be able to operate robotic systems in unknown and dynamic environments. For example, consider this common aerial firefighting example. It's called a firewatch mission, where a helicopter is tasked to figure out where the fire front is. It's tasked to do this by flying along the perimeter as close as possible while ensuring it doesn't fly into the fire. Since the fire is evolving over time, this is a particularly tricky task. There are a number of techniques that have been proposed to be able to address similar problems, for instance, control barrier functions, model predictive control, or path planning techniques. However, all of these have their specific limitations that make it particularly difficult when you have limited perception and the environments are dynamic. The proposed solution in this paper is this algorithm that we refer to as Gatekeeper. Gatekeeper is a safety filter that converts nominal trajectories that are generated by some sort of nominal planner that considers mission objectives into what are called committed trajectories. These committed trajectories are guaranteed to be safe for all future time, and therefore, even in these dynamic environments, we're able to guarantee the system remains safe. Let's now see some of the simulation results that we've obtained. Here we see 3 helicopters starting below the fire and are going to be tracing the fire perimeter. The 3 helicopters are running 3 different controllers, where the black shows the nominal controller that we're trying to target, the blue shows a backup filter controller that is a comparable method to what we're proposing, and the green is the proposed method referred to as Gatekeeper. You can see that Gatekeeper is able to maintain trajectories that are much closer to the actual fire, and as you just saw, it was able to not go into the pocket following the nominal controller because it decided the turning radius was not large enough to be able to safely go into the pocket. The comparable method, the backup filter, remains quite far away from the environment. And that's because of the conservativeness introduced by switching between the backup control input and the nominal control input. Next, here are some experimental results. All of the processing is happening on board a Raspberry Pi 4B. And on the left here, you can see the map that is being built up live in an environment that was previously unknown. Once the quadrotor takes off, this is the map that is being built. And now the cyan trajectory shows the nominal trajectory that has been proposed. Gatekeeper now starts to track this trajectory, and as it moves through the environment, it slows down where necessary to be able to build up a better map and understanding of the environment. Once it has built a better map of the environment, it is able to determine that it is safe to traverse through the window. It goes through the top window, reaching the target point at the end, and now it starts to reverse back out through the window. It's able to do this even though the environment is no longer in its field of view, because it had previously determined that these are safe environments to be able to operate in. Next, the quadrotor lowers to try and go through the lower window, and now you can see that it goes through up to the window, but it determines the window is too narrow for it to safely pass through and prevents the controller from allowing it to go through the window. Thank you.